Today we're going to continue to talk about domination, and then we'll move on to talk about solving 2 by 3 or 2 by 4 or 3 by 2, or in general 2 by n or m by 2 games. So first we'll consider this game with a matrix shown here. It's a 3 by 3 matrix. Player 1 gets a choice of rows 1, 2, or 3. Player 2 gets a choice of column 1, column 2, or column 3. What does it mean for one row to dominate another? Well, in general, what it means for one row to dominate another is that each entry in that row is greater than or equal to the entry in another row. So let's look here. Does row 2 dominate row 1? This 2 here is bigger than the 1 up here, but the 1 is not bigger than the 2, or not even greater than or equal to the 2. Neither is the -1 greater than or equal to the 2. So 2 doesn't dominate row 1, and it's clear 1 doesn't dominate 2. Similarly, 3 doesn't dominate 2, and 2 doesn't dominate 3, and you can check 1 and 3. There's no domination among the rows. What does it mean for one column to dominate another? Well, it means the same thing, only for player 2. Player 2's goal is to get the smallest possible return. So we say one column dominates another if each entry of that column, say column 3, would be less than or equal to the corresponding entry in another column, say column 2. That 2 is less than or equal to that 2. The -1 is less than or equal to the 1, but the 4 is certainly not less than or equal to the 2. So column 3 does not dominate column 2. Neither does column 1 dominate column 2, because the 2 is greater than the 1. And you can check all the other possibilities. There's no one column here which dominates another. What is interesting here is that even though no one row dominates another row, or no one column dominates another column, we can see the following interesting thing. If I look at a mixed strategy for player 2, and we'll label that mixed strategy 1/2, 0, 1/2. That means play column 1 with probability 1/2, play column 3 with probability 1/2, and don't play column 2. I claim that using column 1 and column 3, each with probability 1/2, actually dominates column 2. What does that mean? Well, you can see that 1/2 times the 1 plus 1/2 times the 2 is 3/2. That's certainly less than 2. The 2 and the -1 here, you take the average of those, 1/2 times 2 plus 1/2 times -1, you get 1/2, which is less than the 1. And 1/2 times 0 plus 1/2 times 4 is actually equal to 2. So if we consider this combination of 1/2 column 1 and 1/2 column 3, that's better than, or at least equal to, using column 2 in every row. That means no matter what player 1 does, player 2 is better off playing a mixed strategy of 1/2 column 1 and 1/2 column 3 than using column 2 at all. So that says any strategy at all that player 2 uses that would involve column 2 can be replaced by one where you just use column 1 and column 3 instead, with half the probability that you had previously wanted to use column 2 for. And that will be better, at least if player 1 chooses row 1 or 2, and the same if player 1 chooses 3. So it does dominate. So we say that column 2 is dominated by this weighted average, in this case 1/2 and 1/2 of column 1 and column 3. Because of that, player 2 should not choose to play column 2 at all. So we can reduce the game. Imagine we just eliminate column 2 here from the picture. We can reduce the game to this new game. These are the same column 1 and column 3 from the previous game, and ask how should the players 1 and 2 play this game. And if you look at the game with this matrix, again you'll see that there's no domination among the rows, and there's no domination here among those 2 columns. So in order to solve this game, we're going to develop a slightly new technique. We're going to ask ourselves, what are the expected returns if player 2 plays column 1 with probability Q, and then of course column 2 will be played with probability 1 minus Q. And we ask what's the best choice of Q for player 2. And when we ask what's the best choice of Q, we want to know what value of Q will give the best possible worst case scenario for player 2. Best possible, of course, means smallest value for player 2, since all the payments are from player 2 to player 1. So you want the smallest worst case, which is the smallest maximum return here that player 2 can achieve. And when I say maximum, that means among the possibilities that player 1 has. So we want to find the smallest value which player 2 can guarantee that he or she receives, or that he or she will actually pay out, I'm sorry. And it's easy to compute these. We can say, given this choice of column 1 with probability Q and column 2 with probability 1 minus Q, if player 1 plays row 1, what are the expected returns? Well, the expected return would be 1 times Q plus 2 times 1 minus Q. So we have 1 times Q plus 2 times 1 minus Q, which is easy to simplify. You end up with 2 minus Q. You have Q here plus 2 minus 2Q. What if player 1 plays, instead of row 1, let's change this to row 2. What is the expected return now? Well, the expected return would be this 2 here times Q plus negative 1 times 1 minus Q. And that's easy to see. It'll be 2Q plus another Q, so we have 3Q minus 1. And of course, what happens if player 1 plays row 3? The expected return would be 0 times Q plus 4 times 1 minus Q, which is just 4 minus 4Q. So that means, depending on the choice for player 1, the expected return will be one of these three things: 2 minus Q, 3Q minus 1, or 4 minus 4Q. And remember here, these probabilities, Q and 1 minus Q, are always between 0 and 1. They're probabilities for player 2 to pick column 1 and column 2. So let's put a chart. Let's graph these three things on a chart in a very simple way. Let's say the horizontal axis represents Q, with 0 here on the left and 1 here on the right. And let's graph 2 minus Q. So here's 2. And the graph of 2 minus Q looks like what? Well, when Q is 0, we're up here at 2. When Q is 1, and I know the scales are different on the two axes, that won't make a difference here. That'll keep things very readable. When Q is 1, we're down at 1 here. So 2 minus Q looks like this line here. And so I'll mention this is row 1. Now let's graph the 3Q minus 1. That starts at minus 1. We'll put 0 up there. It starts at minus 1 when Q is 0. So it starts down here. And when Q is 1, we're all the way up at 2. And finally, let's graph 4 minus 4Q. That starts way up at 4 and goes down to 0. And here we have to be very careful to graph this properly. It looks something like that. And so let's see, this was row 2. And the one we just drew was row 3. Now, when we look at this, how should player 2 interpret this? Player 2 wants to have the smallest possible worst case scenario. So in other words, he wants to find the smallest expected return, because small is better for player 2, the smallest return that he can guarantee no matter what player 1 does. How's he going to do that? Well, if player 2 plays a value of q like this, then player 1 might play row 3, and the return would be way up there. If player 2 plays a q, say here, it looks like, again, row 3 would be the highest. If player 2 plays a value of q here, that might be right at the intersection point there, and that would be the worst thing that could happen, and that might be either row 2 or row 1. If we look at, and let me use a different color here, if we look at this upper hull here of the figure, for any value of q that player 2 would play, the worst thing that could happen would be for player 1 to play the correct row that brings the value way up here. So how do we minimize the worst case scenario? We find the smallest vertical coordinate here of any point along this green curve. And this green curve, of course, consists of a union of these line segments. And the smallest point will either be at this intersection point or this intersection point. It looks like the one on the right, and that's what it'll turn out. But we can compute these exactly. How do we find these intersection points? Well, this intersection point on the left is where this line that comes from the values of row 1 here intersects the line here that comes from the expected returns from player 1 picking row 3. And if we look at row 1 and row 3, that's this one and this one, we ask for which value of q are those two equal. That would correspond to this q right here. So we solve, here this is for row 1 and row 3, we solve 2 minus q is equal to 4 minus 4q, and that's easy to solve. You get 2 over here, and you get 3q here. Q equals 2/3. So this is where q equals 2/3. What about for the one on the right here? Well, that's where the return from row 1 is the same as the return from row 2. And if we want to find that, we just have to solve the return from row 1, which is 2 minus q, equals the return from row 2, which is 3q minus 1. And that's easy to see. We'll get 4q on the right, and we get 3 over on the left. Q will be 3/4. So I'm just going to label the 3/4 here. We can ask, what are these expected returns at those points? Here the return is what we get when we plug 2/3 into row 1, the row 1 formula, or of course the same thing for row 3. We plug in 2/3, get 2 minus 2/3, we'll get 4/3. That's the y coordinate here, 4/3. What about in row 3? You'll see you get the same thing. If you plug in q equals 2/3, you get 4 minus 8/3, which is again 4/3. What about at this point? What is the y coordinate? Well, we plug in 3/4 to either row 1 or row 2. You get 2 minus 3/4, and you get 5/4, which, as you see, really is smaller than 4/3. And you get the same thing, of course, if you plug in q equals 3/4 to row 2 as well, because we found that value q equals 3/4 to give us that intersection point. So this point here is the point where q equals 3/4 and the expected return is 5/4. What does that tell us? That tells us that the smallest number, the smallest, in this case, payout from player 2 to player 1, that player 2 can guarantee nothing worse than, is 5/4, and that can be guaranteed by picking a value of q equal to 3/4. So that tells us q's minimax strategy, player 2's minimax strategy is to play Q equal 3/4. Then, of course, 1 minus Q will be 1/4, 1/4. That means 2 should play column 1, or should play a strategy, column 1 with probability 3/4, and column 2 with probability 1/4. Now, with this strategy, in what way does player 1 do the best? Well, if player 1 plays either row 1 or row 2, the expected return will be exactly 5/4. If player 1 happens to play row 3, then that would be even better for player 2, but player 1 would know this and avoid playing row 3, knowing that this is the minimax strategy for player 2, and player 1, by playing either row 1 or row 2, will get a return of 5/4. How does that relate to the original game that we had? Well, let me erase these here for a second. In this original game, we had already eliminated row 2, column 2, so this first column here was what we called column 1 before. So player 2's strategy, and this is the minimax strategy, is to play this first column with probability 3/4. Now we'll put back in the 0 for the second column because that was dominated. And then we have column 3 with probability 1/4. The value of the game, we should mention, will be this number 5/4. Player 2 can achieve that, as we said, by playing the strategy listed above. How does player 1 achieve that? Well, we've said that for player 1, to get to that minimax point, player 1 won't even play row 3, so we basically just solve this 2x2 game, 1, 2, 2, -1. That's just the first 2 rows. And again, you can see, just using the formula we derived in the last video lecture, that the value of this game will be exactly 5/4, and you can find the probability. I'll leave that to you guys. You can find the probabilities that player 1 should use to play row 1 and row 2.